Welcome to Tech for Novice channel dedicated to technology-related information in simple language. Cameras and targets are stationary in most of infrared inspections cases, and they are good enough with still images. They don't need to consider problem with smeared images due to camera movement. However, we need different approach for inspection of kilometers of railway overhead lines. For an example, shooting thermography video with a camera mounted on a vehicle moving along the track is a possible solution. Cameras mounted on vehicles are necessary for inspecting objects over long distances or large areas. The problem with cameras mounted on vehicles is the possibility of blurry images called motion blur. In most cases, we should avoid motion blur, although in some cases it is necessary for special effects. Understanding the motion blur or smearing mechanism is the key to avoiding it or limit to acceptable level. This is an example of radiometric video of overhead catenaries inspection recorded by an IR camera mounted on a wagon traveling 120 km per hour. Obviously, inspecting hundreds of kilometers of such overhead lines is not possible by taking snapshots with a stationary camera. Risk of smeared image due to motion blur is a common problem associated with photography, especially with vehicle-mounted cameras such as satellites, aircrafts, drones, and wagons. Smearing problem is more acute with thermography cameras due to lower frame rate and lower image resolution. If all light coming from a single point of the target falls on different points on the sensor, usually due to relative movement between camera and target, then the target may appear on different positions as trailing blurred copies on the same frame. Such blurred images are the smeared images we are going to explore here. Sensor may not be able to capture full details if the object is moving too fast relative to the camera. Therefore, trailing images could be dimmer depending on signal acquisition time for each position. Image appears sharp if the trailing images are very close to each other. Degree of smearing depends on the relative speed of the camera with target distance, and exposure time. We are limiting our study to motion blur in this video, ignoring other reasons. Let us use 4 stationary cameras with different frame rate to film a moving target. Each colored square represents IFOV of the camera, which is equals 1 pixel. Please note that IFOV is spatial resolution, which defines how detailed objects are in an image. Camera 1 is fast enough to capture each position of the object, instantly creating sharp images. Initially, camera 1 has already captured first frame, and other there are partially exposed as they are slower, taking longer time to complete the exposure. After object has shifted 1 IFOV distance, camera 1 has captured second frame, camera 2 captures first frame with exposure from 2 IFOV sections. Cameras 3 and 4 are still collecting signals for the first frame. After object has shifted 2 IFOV distance, camera 1 has captured third frame, camera 3 captures first frame with exposure from 3 IFOV sections. Camera 2 and 4 are being exposed for second and first frame respectively. After object has shifted 3 IFOV distance, camera 1 has captured fourth frame, camera 2 captures second frame again with exposure from 2 IFOV sections. Camera 4 captures the first frame with exposure from 4 IFOV sections. Camera 3 has started exposure for the second frame. With our example of color-striped object, image colors similar to the target colors means sharper images, more difference, more smearing. Images taken by camera 1 match object colors as they have no overlapping pixels. Images taken by other 3 cameras are those still striped, but their colors don't match the object colors at the position images were captured due to exposure from more than 1 overlapping sections having different colors. It is obvious that smearing is more likely if camera frame rate is slow, speed relative to target is high, and IFOV size is small. In our example of railway overhead lines, target is stationary and camera is moving. Let us calculate the smear size, which is the distance image pixels are shifted during 1 frame time. In other words, it is the distance between the first and last appearance of the same target point on the same frame. As distance equals speed multiplied by time, delta x equals v times tf, where delta x is the pixel displacement, v is camera speed, and tf is frame time or exposure time. If the displacement is divided by linear IFOV, we get number of pixels displaced. If n is the number of pixels displaced and I is linear IFOV, then n equals delta x over I. by substituting delta x with v times Tf, n equals v times Tf over I. Now we can calculate smear size delta x and smear factor n, denoting the number of overlapped pixels. Practically, smear factor n is greater than 1 and acceptance of deviation depends on intended use of the image, viewing distance and display or print resolution. Deviation may be unnoticeable if it is too small. In professional photography, smear factor of less than 1 might be considered acceptable, while in other contexts, a larger deviation might still be perceived as sharp. Smear factor calculator can be used to determine allowed speed of the camera for acceptable image quality. I am not sure what value of smear factor n is acceptable as sharp enough image in thermography. I am assuming image is acceptably sharp if smear factor n is less than 1. This Excel table calculates the smear factor or number of pixels movement during snapshot operation. You may recreate the calculator with the formulas shown here. Variables we need are: speed of the vehicle camera is mounted, camera frame rate of integration time for exposure or snapshot time, and camera FOV, and number of detector pixels to calculate linear IFOV. Please refer to the video Thermography for Novice Part 5, FOV and IFOV calculator for beginners for FOV and IFOV calculation, whose link is given below. Smear factor provides a quantitative score that correlates with human perception of image quality or degree of smear. Attached table shows smear factors for a camera with FOV 80 degrees and number of pixels 640, calculated by smear factor calculator. Even running at slow speed of 10 km per hour, camera frame rate should be at least 425 Hz to achieve smear factor less than 1 for a target at 2.5 meters distance. It impossible with most of the IR cameras available in the market. Let us review recording conditions of the thermography video displayed here. Speed of camera-mounted wagon 120 km per hour. Detector pixels 320, frame rate 50 Hz, FOV 24 degrees, and catenary distance from camera 3 meters. Calculated smear factor is larger than 167, which means displacement of more than 167 pixels. We can safely conclude that smearing can't be avoided by using cameras with such low specifications at such high speed. Measuring accurate temperature is impossible with such smeared image, but the railway company using this camera was quite happy with the outcome. Moral of this example is that thermography is a useful tool even in situations accurate temperature measurement is impossible. Low Earth orbit satellites fly at very high speed of about 28,000 km per hour to maintain their orbits. Then why the satellite images are not smeared? Do they have very short exposure time to capture sharp image at such high speed? Here is data from typical low Earth orbit satellites. Exposure time is relatively short but not in microseconds. The clue is distance, as the altitude of the low Earth orbit satellites are from 200 km to 2,000 km. Longer the distance, larger the linear IFOV, smaller the smear factor. Drones fly at much lower height than satellites and therefore have smaller linear IFOV. But drone images are sharp as their slower speed compensates smaller IFOV. Let's see how a typical drone camera performs. The smear factor is higher when flying at low altitudes and shooting at a slow frame rate, thus increasing the likelihood of blurry images. Thank you so much for watching this video. If you like this video, please comment, share, thumbs up, subscribe, and press the bell icon.